All right, so welcome to the machine learning R tutorial. We are going to get started by loading a whole bunch of packages. You will probably have to install a lot of these packages. The list of what you probably don't have installed is in the course notes, but for the time being, I'm going to assume that you know at this point how to install a package. So we're going to load the Tidyverse library, and this will help us work with our data frames, manipulate data in all kinds of useful ways. We're going to work with the rpart library, and that will allow us to do a lot of our k-nearest neighbors and the partitioning between subsets of data. Rattle is a way to visualize data. Our color brewer, I thought we were going to use, we might not actually use, but it's a great series of color sets that actually draws on the color brewer website. The class library and the facto extra, which will also help us with visualization. It came to my attention that some people may not know this trick, but I'm going to hit Command Enter on each one of these lines. And it will automatically take me to each row just by hitting Command Enter. All right, so you have all of your packages loaded. And just to be totally clear that this is meant to be a very high-level overview of what you can do. We're going to work with numerical data in 3 different ways. The purpose here is not necessarily to make you a data scientist, because this is one tutorial about an introduction to machine learning in R. But what this will hopefully allow you to do is use machine learning to solve problems, to know when you should use a machine learning technique to solve your problem, and give you the foundation to learn more on your own. So we're going to do 3 things. We're going to do classification, regression, and clustering. There are major machine learning techniques that have been omitted from this lab, and that's on purpose because this is just an introduction. So we're going to start with regression. And we've already had an entire lab on regression, so this will really just be a refresher. And the goal overall with regression is to learn a pattern in your data and then situate a new point within that pattern, or to predict new instances based on outcomes that we already know. So we use a whole bunch of predictor variables. That's what we use to build our prediction. And then we have outcome variables, and that's whatever comes out from our prediction, whatever we predict to happen. So we're going to start with basic linear regression. Again, this should just be an overview. This means that I have one predictor variable, and I'm trying to predict one other thing from it. So basic linear regression. I'm going to use some data that's preloaded in R, and I'm going to use the Texas housing data. Texas housing. And this is just a data set that has a lot of information about sales and the value of sales and how long it takes to list all of the houses on a market. So if I go Texas housing, you get a whole lot more information over here. The number of sales, the date, the median sale price, that kind of thing. We want to ask, well, before we want to ask, we should look at what this looks like. So let's do a summary of the Texas housing data and Command Enter there. And what we see is that our city variable is a character. Our year, it looks like this goes from 2000 to 2015. It looks like there's no NAs for our year. It looks like the number of sales goes from 6 to almost 9,000, although there are quite a few NAs in this data set. The volume, which is the total value of all sales on the market, looks like we have the same number of NAs there. We have the median value of a house, the number of listings, the inventory, which is the number of months. It would take to sell all the current listings at the current price, which is obviously predicted from other variables, and the date. All right? So that's our housing variable, or our Texas housing data set. Now, if we look at how this is structured, Texas housing, it looks like we have our city, our year, the month, the number of sales, the volume, all of these things. Okay, that's about what we would have expected. So I'm going to make a linear model. And the question I want to ask is, what is the median sale price based on the number of listings? So can the number of listings predict what the sale price is going to be? I have a hypothesis that the more listings there are, the lower the median sale price. Let's see if that can be borne out from what we have. I'm going to call my model LM housing. I'm going to assign it to LM and then median by the listings, because again, I'm predicting the median sale price from the number of listings. And the data I want to use is the Texas housing. We'll run that, see how it goes. And it looks like I have a typo. That should be listings rather than listing. Go ahead and run that. There we go. All right, so it just shows us that LM housing was created, but doesn't actually give us any information. If we want to know some information about it, we go summary, LM housing, run it, and we see that it did work, and we have our equation down here. Okay, so we're going to hold off on looking too deep into this, because my real goal here was to find out how much a new house would be that has a column named the exact way as the other variables. So I want to know, if there are 800 houses for sale, how much can I get for my house? So my unseen data set is going to be a data frame, and listings with an S is going to be 800. All right, so I have this new data point. I want to find out how much my house will sell for if I know that there's 100 or 800 listings out. And then I will predict what I get using the LM housing model with my unseen data. And I'll run the both of these. And it looks like, based on this model, I could sell my house for $127,000. Excellent. So now I have an idea of how much the median selling price would be based on the number of houses that are listed. Now, my question is, should I trust that model or not? So you remember from our previous video that the way to figure that out is to ask for the summary of your model. We go and look for the r-squared value. And it looks like our multiple r-squared value is 0.06, which is nowhere near 1. And if we remember, a very high r-squared value, so a value near to 1, is an excellent model. And a very low r-squared value, or a value near to 0, is a terrible model. So it looks like we can't actually predict the value of the houses based on the median, the number of houses that are listed. Right? So I'm going to have you take a minute and go ahead and answer this question. Is there another variable that is a better predictor of median housing price? Some of these variables are not candidates for prediction, and why wouldn't they be a candidate for prediction? But some of these variables may give us a better sense of how much we can list our house for. Right? So take a couple of minutes and then we'll come back and work on multiple regression. All right, so it is clear that our model here was far too narrow. It's probably the case that there are other factors that affect the sale price, but it's more likely that external factors to this data set, like square footage, condition, would impact it more. In order to deal with all of those variables, we would need multiple regression. So we would need more than one input variable or more than one predictor variable to help us get an idea of how much we can sell our house for. So unfortunately, the Texas housing data doesn't have the information we're looking for. So we'll get some data from StreetEasy. So there's a data set that's loaded into the LMS called streeteasy.csv. And I'm going to load that in here. And I'm going to call it street. And I'm going to say read.csv and figure out where I am right now. I am here, so I'm going to navigate in my computer to where this data set is. Right, and then, so wherever you saved it is where you will find it from. All right, so we'll run that, and then we'll ask for a summary of the street there. And what we get is a whole lot more information. So we have things like the rental ID, the rent, the number of bedrooms, the number of bathrooms, minutes to the subway, all kinds of data points or all kinds of variables that are probably going to be way more interesting than the number of units that are available, right? Because, I care more about the number of bedrooms than how many other houses are available. All right. We're also looking at New York City. So we are looking at a different data set. We're looking at apartments, not houses. All right. So I'm first going to select some of these variables. I don't want all of them, in part because things like neighborhood and submarket are going to be really hard for me to visualize. And I probably don't want to deal with them. Likewise, the things that we would assume matter the most are the number of bedrooms, the number of bathrooms, the square footage. I'm going to assume that minutes to the subway matters because if that's what most people's transportation is. The floor, are you on a 4th floor? Are you on the 20th floor? And the building age in years. You would assume that an older building would be less expensive than a newer building. All right, so I'm going to just select 6, and I'm going to call it street select 6. Okay, and then I'm going to assign that to street, which I will then pipe over to select. My pipe didn't work. I'm going to select rent, because that's what I'm trying to predict. The number of bedrooms, the number of bathrooms, the size and square footage, the minutes to the subway. I'm going to hit enter here, just go to a new line. The floor, and the building age in years. I'll run that, and unexpected symbol here, which means that I have a typo, right? Oh, because there's no comma in between these. Got it. All right, there we go. So we've selected these 6 variables and our 1 outcome variable. So we have 6 predictors and 1 outcome. All right. So now we're going to build a model from these predictors. And I'm going to call it LM Street 6, or LM Street Select 6. And I'm going to assign it to the linear model of rent based on all of the other variables. So I'm just going to use a period. My data is going to be the street select 6 that we just made. I'll run that and ask for a summary. And we can see here, if we run this, that we have a whole lot more information. All right, So here our residuals are median of the residuals. We're not going to worry about that right now. But we have all of these variables here and what each one means. So the code, the stars that you see over here is the degree to which it's significant. So 3 stars means it's significant at the 0.001 level. And if we remember back to our normal curve, that means that you can assume that this is a contributing variable and this contributes significantly to the model that we've made at the 0.001 level. So it means it's very, very significant, that it's not by chance that this variable matters. If we had just 1 star, it would be 0.05, which is typically the cutoff for reporting significance. So all of the variables that we have here are statistically significant. And it looks like they're all significant at different levels. So we have these 2 times 10 to the negative 16th, which is an incredibly small p-value here. And what that means is that all 4 of these contribute equally. So bedrooms, bathrooms, square footage, and the floor that it's on contribute equally to how much the rent is going to be. Minutes to the subway contributes the least. It's 2 to the negative 5. That's quite a bit larger than these other ones. Building age in years contributes somewhere between the 2. It looks like it is very statistically significant, but maybe not as much of an impact as something like bedrooms or bathrooms. All right? So what this tells us is that all of these should be retained. So I'm going to have you go ahead and explore this data set on your own a little bit and make models for other combinations of variables. The first model will be one that only takes square footage into account. And the second should be a model that takes everything except neighborhood, submarket, and borough. And the template code for figuring out how to make these models is in the handout. So go ahead and follow that and fill in the blanks as you go. And after you look at all of these, go ahead and compare the R-squared values to figure out which one is the best predictor overall. A little bit more advanced version is to use the adjusted R-squared, which takes into account the fact that you have multiple variables. And you'll notice that the adjusted R-squared, when we have just 6 variables, is just slightly lower than the multiple R-squared. You'll see when you have up to 16 variables, there'll be an even bigger difference between the multiple and the adjusted, because the number of variables in your model increases the uncertainty and therefore decreases the predictive power of the model. So compare all 3 of these R-squared values and figure out which one has overall the best predictive power to tell us how much rent will be in New York City. All right, so now we're going to move on to decision trees. Decision trees in many ways are one of the least glamorous machine learning techniques. And that might be in part because they're so interpretable, but they also might be one of the most useful machine learning techniques because they are interpretable. And as we discussed in class, we are very much in a moment of needing considerably more interpretability in order to trust our algorithms to create the future that we want to. So if I can give a plug for the decision tree, I'm going to give one right now. All right, so we're going to do some classification. We're going to use the Titanic data set. It's a classic example. Who survives, who dies. All right, but we're going to use the version distributed by Kaggle that has already been broken into a training and a test set. So we have a set that we're going to learn our tree on. That's our training set. And we're going to have a set that we're going to assess our tree on. That's our test set. Okay? So I'm going to load in the training data set, and that is read CSV, and then go to my desktop and the data sets. You will find this wherever yours are at. And it's just called train. It should probably be called something. Oh, it's in the Titanic folder for me. And it's just called train. Probably should be called something a little bit more descriptive. I'm going to copy this because that was really annoying to type. And I'm going to paste it. I'm going to call this test. And we're going to use the test CSV. Okay. So go and run this one and run this one. And I've loaded my training and my testing sets in. And I'm just going to make sure that they look how I expect them to. So I'm going to ask for the structure of test and the structure of train. And if I look at them both, they look exactly the same. It's just that this one has 400 observations and this one has almost 900 observations. This is a really big test set. Generally, when you're doing machine learning, your test set is something like 10 to 30%, not almost like a third of your data. But it's a pretty robust way to get validation. You'd want a big test set like this when you're building a model that is going to remain relatively static. And as we've talked in class, you make different decisions based on your goals. All right. We see that we have a whole lot of variables, 12 variables, many of which read in as factors, such as male and female, ticket types, things like that. We're only going to use a few of these variables today, but feel free to play around and see if you can predict better using some other variables. All right. So I'm going to only select the class, the sex, the age, and whether or not they survived. So I'm going to do that for my training set, and I'm going to do that by calling the training set, piping it over to select just P class, sex, age, and if they survived or not. And then I will do the same exact thing with my test set. I'm going to do that by copying and pasting. If you get really advanced with R, you might write functions that you can then use to do things like this because it can be kind of tedious, but that is unnecessary when you're just doing two. All right, so we have selected just the class, the sex, the age, and whether or not they survived. So I am going to make a tree. I'm going to call my tree. And I'm going to assign it to, or I'm going to call our part on survived as predicted by the P class plus age plus sex. You could have used a period here, but I wanted to show you the other way to do it. And I'll have I want to call it from train, and the method is class. In quotes. Right. So now we're going to visualize that with a fancy R part plot tree, which I already typed out there. All right, and we're going to pass the fancy R part plot, our tree model that we created here. And the reason that we chose the class method is that each one of these variables is a factor variable. So anytime you have factor variables within your partition, you're probably going to want to use the class method. You can look at other methods in the RPart documentation. All right, so we will run that and we'll get our fancy tree. And what we see is this kind of elaborate but exceedingly useful decision tree. Each node represents a decision that helps lead us to our outcome. So there's a lot of information communicated at each node. The first thing that you see here up at the top is what the dominant class of everyone who passes through this node is. So the dominant class of everyone who passes through the node is 0, so they did not survive. All right, from this first node, it's sex. So if the sex is male, yes, we go to the left. If the sex is male, no, we go to the right. This yes on the left and no on the right is going to be replicated for every single node in our tree. The other thing is at the bottom here, you see how much of the data passes through this node. The top node, obviously 100% passes through this node. Here, only 65% pass through, 35% pass through the other branch. All right? So, if we look at this and we try to find out how much, if a female in third class over age 39 would have survived. All right, so we start here, and sex is male, no. Class is greater than 2.5, yes. Age is greater than or equal to 39, yes. Would have survived, 92% chance of survival. And this represents 1% of the data who's landed here. All right, so that's great. And we can use our tree to interpret the relative strength and what each branch contributes to the final outcome. But this tree on its own doesn't tell us how well it's performed. To understand that, we have to test it. We're going to use that testing set that we partitioned out earlier. All right, so we're going to call our variable pred, and it's going to be a prediction based on our tree of all of the data in our test set, and the type is going to be equal to class for the same reason that our method was equal to class, because we're talking about factors. All right, so we run that, and that doesn't really tell us much. If we see what the pred variable actually is, it's what would have been predicted for every single element in our entire data set. So 418 predictions. That's not actually that useful. What would be far more useful would be something called a confusion matrix. And a confusion matrix is a table of the real and the predicted outcomes. So I'm going to calculate a confusion matrix. I'm going to use a table, and from the test set, I'm going to use the column survived and the predicted outcomes from that. Okay? And then I'll run that and see what my conf looks like. And I have my test labels. So this is what was actually true, and our predicted labels. So this is what our model predicted. And this looks like our model predicted 184 people to have died who actually died. So 184 true negatives and 25 false negatives. So our model predicted 25 people to have died who actually survived the accident. If we go over here, our model predicted that 20 people would survive who actually died, and 102 people who would survive who did actually survive. So 102 true positives. We can use confusion matrices for a lot of things. To calculate the accuracy, which is something that a lot of people find to be more useful, we actually need to calculate the diagonals. Likewise, to calculate the precision and the recall, which is the actual use of a confusion matrix, we want to isolate each one of these variables. So, all right, so to find my true positives, I'm going to take the confidence of item 2, 2. So this is items that were predicted 1 that are actually 1, and this is position 2. This is position 1, this is position 2, position 1, position 2. So I'm going to take conf, and I'm going to find number or item in position 2, 2. For my false positives, I'll take the conf, and in this matrix, my false positives are this 20 here. So it's position 1, 2. We go rows, columns. Right? For our true negatives, this will be position 1, 1, because this is our true negatives, things that were predicted negative that were actually negative. And finally, for our false negatives, we'll take conf, and then that'll be everything in position 2, 1. So this 25 here is row 2, column 1. Okay. I'll run all of these, and that's great. We've stored 4 new variables. But what we actually want to do with this is calculate the accuracy, precision, and recall. So our accuracy is the sum of our true positives and our true negatives divided by the sum of our true positives, true negatives, false positives, false negatives. So everything that was accurately labeled, so everything that was predicted positive that was actually positive, everything predicted negative that was actually negative, over everything at all. Run that, and then print it to the screen. We have 86% accuracy. That's pretty good overall. Generally, machine learning models that perform at better than 80% accuracy are considered to be quite good. Next, we'll look at the precision, and the precision is the number of true positives divided by the sum of the true positives and the false positives. So everything that was labeled positive, whether it was accurately labeled positive or not. Run both of these, it looks like our precision is 0.836 or 83.6%, which is also very good. And finally, we have our recall, which is the number of true positives divided by the sum of the true positives and the false negatives. And this is the true things that were labeled positive that were actually positive, and then divided by everything that was actually positive within the data set. Go ahead and run that, and looks like there's a problem. Oh, right, it's the sum there. Run that, go ahead and print it to the screen, and what we see is that our recall is also quite good at 0.80. All right, so there is a bit of a shortcut to calculating the accuracy. It is to say the accuracy is equal to the sum of the diagonal of the confidence divided by the sum of the confusion matrix. This is just a shortcut that is 100% unnecessary, but saves you a little bit of typing in the end. So I'll go ahead and run that, and you see that it's exactly the same. All right, excellent. So in the handouts, there's a part about an overfit tree. We're not going to worry too much about that. If you do ever need to prune your tree or narrow it down, go ahead and work through that example in the notes. For our purposes, we're going to move on to another classification algorithm, which is k-nearest neighbors. So k-nearest neighbors is really kind of cool. It is based on how close a data point is to others, which allows you to classify that data point according to its distance along many dimensions to other data points in the training set. So we'll see a little bit about how that works. The first thing that we want to do is make sure that our training and our testing sets both have everything removed. So from our training set, we want to drop NA from our training set. And from our testing set, we want to do the exact same thing. We want to drop NA of our test. If there are any null values in your train or test set, this will not work. K-nearest neighbors cannot handle null values. All right, so my training labels are going to be the survived class. So it'll be train, survived. This is the label or the outcome. And my test labels will be the train, survived class as well. And we want to separate these from the rest of the data because we're going to end up using this to validate whether we got it right or not. All right, and then we're going to go ahead and manipulate our sex column. This is a whole lot of code, so I'm going to have you copy it down from the notes, but I'm going to talk you through what's going on here. So the first thing that we want to do is substitute male for 1 and female for 0 for every value in this column. The way that we do that is first by making this column a factor, because currently it's a character value or a character variable, and we want it to be a factor variable. The difference is that characters are read as strings, whereas factors are read into categories. And then we substitute for everywhere that's male is a 1 within this column. And this gives us a new column here. We do the same for female, and we do the same on the test set. The next thing is that we make this 0s and 1s from characters, which they are now, since they're in quotes, into numeric values. And the reason for that is that k-nearest neighbors needs to have a numeric value. So generally, when you're doing a categorical variable, you turn it either into 1s and 0s or give it some sort of ranking system, 0.51, something along those lines, depending on your variables. So this has allowed us to take a categorical variable, male, female, and turn it into a numeric one. Next thing we're going to do is essentially drop this survived column by pointing it to null. We're just going to say, survived, you are empty, right here. All right. So once you've run all of this, you should have a bunch of new variables stored. And we are now going to deal with the fact that the rest of our variables aren't really normalized either. So something like class or age is on a completely different scale from something like gender. So what we want to do is make those into decimal places, which basically says how far along this line is your variable. And again, rather than typing out this code, I'm just going to walk you through it. So we set the minimum for the class variable as the minimum value in the P class. In our case, this is 1. The maximum is the maximum value in the P class variable. In our case, this is 3. And then each item in the P class variable is going to be measured by how far away from 1 it is over how big the range is. So the max class minus the min class. And what this does is gives us a point along a continuum from 0 to 1 where each variable sits in relation to the others. We're going to do the same with the age variable. And one helpful way to think of this is what percentage of the age range is any given individual. So again, we have the minimum age, the maximum age, and each point in the age column is going to be the age minus the minimum age divided by the range. And this gives us a percentage along the continuum of range. And now we can make our predictions based on the k-nearest neighbors. We're going to use 5 just so that we have a place to start. We're going to make a new variable, pred, for prediction, and call the knn function on it. Our knn function always requires a training set and a testing set to evaluate itself on. So we'll have kpred and we'll assign that to k nearest neighbors. Our training set is k nearest neighbors of training. Our testing set is k nearest neighbors of testing. And the class is the train labels, and we'll set k equal to 5. And we'll go ahead and print k pred and run both of these. And we get a whole bunch of zeros and ones of what is predicted based on our model. So let's again make a confusion matrix in order to better understand what's going on with our model and summarize the results. So we'll set conf for a confusion matrix equal to table, and in the table we'll have the test labels and whatever was predicted. So this is the test labels, that label of test survived, and what was predicted by our k nearest neighbors model. And it looks like we have an issue. And I found the typo. I hope that you were following along with the notes rather than my typing. The issue was up here in the test labels at the very, very beginning. I used train survived twice. And the train labels should be train survived. The test labels should be test survived. Run that. That is not something that exists. Test survived. Now, if we go down here and run this, we will get our confusion matrix. And our confusion matrix illustrates to us that this model is not that great. But let's go ahead and use it and see if it can help us predict who survives the crash and who doesn't. All right, so I'll make a new person, and I'll call this person My Titanic. And I will give this person some pre-normalized values. So I'll pass it into a data frame, and I'll say that their age, they're 0.6 along the way, so pretty close to the middle. Their passenger class will be directly in the middle, so they'll be 0.5. Let's say they were second class. And their sex will be female. So their sex will be 0. Run that, and then our new k prediction, which is how we can find one variable, be knn. Our training set will be the knn train. Our test set will be My Titanic, because we want to see about this person, see if they survived. Class will be the training labels, and we'll have k equal to 5. And my new k prediction says that this person survived. Congratulations. All right. There are a lot more classification algorithms such as naive Bayes, logistic regression, and more. We're not going to cover any of those here, but hopefully this has given you an introduction to classification that makes you want to learn more about it. The final thing that we're going to work on today is called clustering. So clustering is different from the previous two methods because clustering is an unsupervised machine learning approach. So if you have a bunch of data and you want to group it together, but you don't really know yet how those groups go together, then you're going to want to use clustering. If you don't have labels, you have to use clustering. So we are going to first set the seed to our algorithm here. Clustering involves some degree of randomness, and therefore in order to create reproducible results, just like with most classification tasks, you need to set the seed. So if anyone would use the same seed, 1, 2, 3, 4, again, they would get the same results that you're getting. All right, so we're going to use the iris data set because it illustrates clustering really well. Even though we already know what the labels are, the reason we want to use it is to make sure that we can actually use clustering in order to get the results that we want. So the first thing that we always want to do is inspect our data set. For us, we're going to use the head. When we see that the first 4 columns are variables that we're interested in, the 5th column is our species. We're going to want to cut that off. So I'm going to make a new data frame, and I'm going to call it my iris. And I'm going to set it to iris, all of the rows, but I only want columns 1 through 4. Okay, I'll run that, and if I look at the head of my iris, I see that the species column has been cut off, just as expected. All right, and then I'll have my species column, which is my actual labels, and that will be just the iris species column. Okay, I'll run that. All right, so I'm going to do k-means clustering. We already know that we should have 3 groups. So we're going to ask R to restart itself 10 times to get the average from 10 different trials. So I'll have k-means iris, and I'll assign that to k-means. I'll pass it my iris data set, and I'll tell it to give itself 3 centers and to restart itself 10 times. Okay. And it's k-means, not k-mean. And it's n-start rather than n-start, whatever that was. All right, so our k-means iris, and if we go ahead and inspect that, what we see is a whole lot of information about our cluster. So it tells us that we have 3 clusters, and there's 50 in the first, 38 in the second, and 62 in the last. Here's the mean of the center of each one of those clusters, and what category each one of those clusters belongs to, categories 1, 2, or 3. It's obviously never going to be able to tell you what the labels are, but rather it'll tell you, this is just cluster number 1, and then leave it up to you in order to figure out the clusters. The within cluster sum of squares by cluster is here. What's more important here is the 84%. This tells us that it's actually quite a good clustering algorithm in terms of internal similarity and compactness, and the distance between each cluster from the others. At this point, though, it would be really helpful if we could somehow validate how well our k-means algorithm performed, which we can. So we're going to use that species column in order to create a confusion matrix with the output of our k-means iris. So we'll call table, and then species are correct values, and then the k-means iris, and then the cluster column. And what we see is that Setosa was in cluster 1 50 times. That's amazing. It must be very different from the others. Versicolor was in cluster 2 twice, but that's probably an error because the majority of versicolor was actually in cluster 3, 48. Finally, there's the Virginica, which had 36 probably correctly put into cluster 2, but then 14 outliers, which were mistakenly put into the versicolor category here. So these clusters allow you to see how groups kind of shape and form. And a couple of them got miscategorized, but it would probably be pretty difficult for the human eye to get them right either. So if we want to visualize this somehow, we can actually plot the result of k-means clustering. You can plot the result of all clustering. It's pretty cool. So we're going to plot petal length as a function of petal width. The data we're going to pull from is my iris, and the column will be the k-means iris cluster, or the color will be k-means iris cluster. Run that, and we get a simple plot here where the cluster that each item has been categorized into is represented by color. So we have black over here. This is definitely our setosa, very, very different from all the rest. And we see here how it's very easy to miscategorize both the virginica and the versicolor because they kind of bleed into each other. So these ones right here are very different, very difficult to categorize. Okay. So that's given us a first view into it, but there's way better ways to do this with the Facto Extra package. And so the function that we want here is fviz cluster, and then we're going to tell it that k means iris, and the data is my iris. And then this gives us a much better clustering where you can start to see the boundaries of each cluster and where, where the algorithm decided that we were looking at versicolor rather than virginica. And each of these points are, and this shows us a lot better the boundaries of our groups and gives us some insight into how those boundaries are created and what points or what rows weigh into those boundaries the most. All right, at this point we are going to move on to unsupervised unknown clusters. Quite honestly, this is quite a bit more advanced than what we've been working on so far. So if you are interested in working with clusters, or if you think that you're going to be doing unsupervised clustering in the future, I highly encourage you to complete the rest of the tutorial where you will make a scree plot and figure out, without knowing anything about your data set, how many clusters you're going to need. And this is what we went over in class, looking for what we call the elbow. All right. There is a exercise at the very end of the tutorial that is super interesting, and it's about US arrests and the US arrest data set. But it goes pretty far beyond a very basic introduction to machine learning. So we're going to stop here. I hope that you are super excited about everything that you can do with machine learning in R, and let me know if you have any questions. All right, take care. Bye-bye.